Good afternoon, everyone. Today's lesson will describe how to balance chemical equations. As you may have guessed, this demonstration supports the California Next Generation Science Standards related to chemical reactions. The learning objective will be to refine the design of a chemical system by specifying a change in conditions that would produce increased amounts of products at equilibrium. Let's get going. So this lesson is going to introduce the method for balancing chemical equations. Can anyone remind me what a chemical equation represents? Maddie? That's right, it's the representation of a chemical reaction. And what exactly is represented on each side of the equation? Luis? Yeah, the reactant is on the left and the product or products are on the right. Great. Go ahead and take out your graphic organizers. We're going to watch a short PowerPoint right now and then get into small groups to solve some practice problems. So back in the early 20th century, a chemist named Le Chatelier discovered some universal truths about chemical equations. After countless trials and math applications, he realized that systems always readjust themselves to obtain equilibrium. It wouldn't matter if there was a change in concentration, a change in temperature, volume, or pressure. The system would always readjust itself to counteract the change. In fact, equilibrium seemed to be the natural state at the quantum level. Using this knowledge, Le Chatelier created a principle that outlined this universal truth, and then he was able to predict concentrations of elements after changes to chemical systems had occurred. The basic tenets or facts that go along with this principle are as follows. Number 1, atoms are not created or destroyed during a chemical reaction. They only get moved around. Second, for equilibrium to occur, there must be the same number of atoms on each side of the equation. And then, knowing this, you can balance the chemical equation by adding coefficients in front of the chemical formulas. However, you can never add or change subscripts. So the process involved in this includes 4 steps. The first, you need to determine the number of atoms for each element. Then choose an element that is not equal on both sides of the equation. Add a coefficient in front of the formula with that element and adjust your counts. And then finally, continue adding coefficients to get the same number of atoms on each element on each side. So the coefficients are the large numbers in front of the chemical formula, while the subscripts are the small numbers attached to the bottom of the chemical formula. You can see right here. Also, as we pointed out earlier, the reactants are to the left of the arrow over here, while the products are to the right of the arrow over here. So, some step-by-step example problems. Step 1. How do you determine the number of atoms for each element? Well, first you're going to look at the subscripts and coefficients. And then you can list them. Step 2, you pick an element that is not equal on both sides of the equation. Since the oxygen atoms are not equal, we'll target those first. Step 3, add a coefficient in front of the formula with that element and adjust your counts. So we have magnesium and oxygen. Adding a 2 in front of the magnesium oxygen will change the number of atoms on the product side of the equation. And then step 4, you continue adding coefficients to get the same number of atoms of each element on each side. Now, we need to increase the number of magnesium atoms so we have the reactants. We have on the reactant side. Adding a 2 in front of the magnesium will give us 2 atoms of magnesium and balance the equation. Here's some practice problems. In the first equation, because the 2 subscript multiplies the carbon as well as the iodine, we will have to add a 2 in front of the potassium iodine to make the iodines equal, like this. But now you have too many potassiums in the reactants. So a 2 also needs to be added in front of the potassium chloride.